Good morning, students. Welcome to the virtual classrooms. In the last lecture, we studied it related to the quantum numbers. Today, we will be studying it something related to shapes of orbitals. Now, actually when we are talking about shapes of orbitals, these shapes of orbitals, they depend upon and one equation which is considered as Schrodinger wave equation. Now, this Schrodinger wave equation, it's given out as del square psi by del x square, del square psi by del y square, del square psi by del z square, 8 pi square m upon h square e minus v psi equals to 0. That is one of the equation which was given by Schrodinger. Don't bother, we don't have to study this equation, or nothing is there for the derivation, or neither even the numericals will be based on it. It's only for your knowledge that this type of equation was there, which was been studied by the scientist named Schrodinger, and actually from that we want to take out the knowledge of it. This is known as psi. It is termed as psi. We will be using it for the study of shapes of the orbitals. Now let us try to understand how it is going to be useful for the shape of the orbitals. Now, when we are talking about the shape of the orbitals, it means where is an electron. This whole study that we are doing it is an arrangement of an electrons, right? So, in an orbital, around the nucleus, how these electrons have been arranged, what is the position of that electrons, that we are finding it out, right? This psi, the moment we just saw it, it's termed as wave function. Wave function of what? R. What is R? Radius. That is distance between the nucleus and electron. It's a wave function. Wave function of R. Psi is a wave function of R. Right? Now, psi it does not have. It does not have any physical meaning. Psi does not have any physical meaning. But if I take it as psi square means alone psi, no physical meaning. But when its square is done, when the value of the wave function of the R, psi, which is a wave function of the R, if it is squared out, it indicates the probability of finding the electron around the nucleus. That means, if I put it, suppose, as an example, this is my nucleus. This is the position where there is a probability of finding the electron. Now, every time we are not going to get the same probability, right? Wherever the probability of finding the electron is maximum, wherever the probability of finding the electron is maximum, that we have plotted, and that is considered to be as an orbit, right? Every time in the nucleus we are not going to get the same probability. If suppose for the first orbital I am getting it over here, then for the second probability might be somewhat away from the nucleus. So wherever the probability of finding the electron we are getting it, we consider it as an atomic orbitals. We consider them as atomic orbits. Now this probability of finding the electron around the nucleus will give me the shape of the orbitals. At the same time, the word we used it, that here we told that there is a maximum probability of finding the electron. But what about this place? The probability of finding the electron is not there at all. So this particular place we termed it as nodes, or the word we used it for it as nodal plane. It is considered as a nodes or nodal planes. That means the definition of it, the probability of finding electrons around the nucleus is 0. The plane is known as nodal plane, and numbers are known as nodes. The total numbers with that we calculate, we term them as nodes, and such type of planes, whatever we get it, we consider it as nodal planes, right? So this is the factor. Now again, the nodal planes or the nodes that we are calculating it, how can we come to know it? So for it, the another factor or the formula that depends upon our quantum number. There are two types of nodes. Radial nodes and angular nodes. Now, when we want to calculate the radial nodes or angular nodes for any given orbit, we are having it as a formula. Radial nodes are n minus l minus 1, while angular nodes are given as l. Radial nodes means n minus l minus 1, angular nodes means l. That means if I want to calculate the total number of nodes, we get it as n minus 1. Okay, now this factor we want to study it because it can be our one of the objective question, right? We can be asked what are the radial nodes, what are the angular nodes, what are the total number of nodes present in the given orbital. So first of all we'll try to understand how to calculate the nodes, and then we'll come back to the shapes of the orbitals. First of all we'll try to understand these types of nodes. Radial nodes, that is the probability, these values, radial nodes, they are variable for given orbits. These are fixed because its value is L. Let us understand it. Suppose if I am asking you 1s. Now 1s is one of the orbital that we will be naming it on the basis of the quantum numbers. N, L, M, S, we studied it. In it we wrote it as 1s. So how many radial nodes are there? Radial nodes. That means n minus 1 minus L minus n is here for n 1, L 0. So n minus L minus 1, 1 minus 0 minus 1. So we will get it as 0 radial nodes. If we calculate it as angular nodes, we will be getting it 0, right? So we got it as in radial nodes 0, angular nodes 0, and if we calculate the total number of nodes, we get it answer n minus 1, that is 1 minus 1, 0. This is nothing else. The total number of nodes are nothing else but radial plus angular. 0 plus 0. We got it, the answer 0. Right? But that is for the 1s orbital. This is for the 1s orbital. That means if you plot a nucleus, around the nucleus where you are putting it, the electron, probability of finding the electron, the 0 probability of finding the electron, the plane where we can't find the electron at all, there are no such type of planes present in it. So 1s orbital do not have such nodes. Now if I go it for, in place of 1s, the values are going to be changed. If I go it for 2s, that means n is equals to 2, L is equals to 0 for 2s. That means what will happen? Our value will change from n to L 0. 2 minus 0 minus 1 is 1. Angular node. Angular node is going to remain 0. Right? While total number of nodes, we will be getting it as 2 minus 1, that is 1. 1 plus 0, 1. Again, in this was 1s orbital. If I am plotting it, the 2s orbital around it, there is a one node that is present, or one nodal plane that is present between 1s and 2s. Let's take it as 3 for it. We will be getting 3 minus 0 minus 2, that is 2, or 3 minus 1 is 2. Right? So what will happen? We will be having it as an 3s orbital. We will be getting it another nodal plane. So in common for ns orbitals. Now in place of 1s or 2s or 3s, if I am going, we wrote it just for 1s, total nodes 0, 2s 1, 3s 2. So for, suppose if I want to write it for ns, what will happen? We can write it as ns will have n minus 1 nodal planes. That means 1s, 1 minus 1, 0. Here total nodes n minus 1. So 0, 1, 2, we will be getting it as n minus 1. These are the all known as radial nodes. These are all going to be radial nodes because our angular nodes for the s orbitals are always 0. Let us similarly go it for p orbitals. Now going it for the p orbitals, what we will be getting it? We want to calculate the radial nodes, angular nodes and total nodes. Let's take it as 2p orbital. That means what will you get it? This is n minus L minus 1. That means here we are getting n equals to 2, L1. So we will be getting it as 2 minus 1 minus 1, that is equals to 0 nodes. While angular node is L, that is 1 node. So total number of nodes we will be getting it as a n minus 1, that is 2 minus 1, that is equals to 1. 0 plus 1, we got it as 1. So for the p orbital, what we got it? Angular node for the p orbital 0, but whereas for the angular nodes we got it 1. So total number of nodes are 1. Now in place of 2p, let us take it as 3p. In 3p what will happen? Radial nodes, we will get it as 3 minus 1 minus 1, that is equals to 1. Angular nodes, we will be getting it as 1. So total nodes, we will be getting it as n minus 1, that is equals to 3 minus 1, 2. 1 plus 1, 2. So if anyone is asking me, what are the number of nodes that are present in NP orbitals? So in that case what will happen? NP means n minus L minus 1. That means I will be getting radial nodes for NP orbitals as n is as it is L1 this, so we will be getting it as n minus 2, whereas angular node, that is fixed 1. So total nodes, we will be getting it as 2 plus, n minus 2 plus 1, that is n minus 1. We will be getting it as an n minus 2, that is radial node. Angular node 1. So total n minus 2 minus 1, that is equals to n minus 1. Right? So that is for the p orbital. So from this again we can see it, our radial nodes, they are changing 0, 1, n minus 1, 2. Radial nodes are changing, but when I am going it for angular node is fixed for it. That is one angular node for it. Right? Okay. Similarly, if I go it for d orbitals, if we calculate it for d orbitals, let us take it as, we know it that it always starts from 3D. We can't have it as 1D or 2D orbitals. We always get it from the 3D orbitals. We saw it in the quantum numbers. Now 3D orbital. So what will get it here? N3 L, that will be 2. So that means our angular nodes are fixed. Angular nodes have been fixed. They are 2. Radial nodes, we will be getting it as 3 minus 2 minus 1, that is equals to 0 for 3D. So according to the formula of n minus 1 for the total nodes, we will be getting it as 2 nodes. And both of them are going to be angular nodes. Now, if I go it for 4D orbitals, we will be getting it as radial nodes, that is equals to 4 minus 2 minus 1, that means 1 radial node, angular node 2, total nodes, we will be getting it as 3. Let's check it. According to the formula, 4 minus 1, that is 3. If we take it as 5D orbitals, radial nodes, 5 minus 2 minus 1, 2, angular nodes, we will be getting it as 2. So total nodes, we will be having it as 4. Right? So like that, you can calculate it for any given orbital. For any given orbital, you can calculate its angular node or radial node or total number of nodes, whose general formula it's given out for any given orbital as, for radial nodes n minus l minus 1, angular nodes l, and for total number of nodes n minus 1. Right? So this can be one of the objective question to calculate the nodes that are present in it, or if total number of nodes are this, how many number of angular nodes and how many number of radial nodes are present in the orbital. That can be one of the objective question for you. Right? Okay. Now, once we come to know it, the nodes, that is the probability of finding the electron around the nucleus is 0. That are known as nodes or nodal planes. Now let us see the shapes of it. Now this probability of finding the electron, once we came to know it, what we will come across? First of all, s orbitals. First of all, we will go it for s orbitals. And in the s orbitals, what we are going to get the shape? Shape is spherical. That means nucleus, and around the nucleus, this is 1s orbital. Right? It's a nucleus, 1s, around it 2s. So we are getting it as one nodal plane. The continuous circle that is being plotted, it's considered to be as an orbit. The probability of finding the electron is maximum atomic orbital. So as we are going to get it as spherical. When we wrote it as p orbitals, we are going to get the shape as we are going to write the p orbitals as dumbbell shape. Now why it is written as dumbbell shape? Then for it, it's a two-dimensional figure, right? When you plot it as in three-dimensional, these axes which I have plotted, it's slanting. You have to consider that it's going from top to bottom. It's going from front to back, right? But it's not possible to be drawn on the board, so I have just placed it. These axes, we are going to consider it as x, y, z. These are the x, y and z. The probability of finding the electron is maximum on the x-axis. The probability of finding the electron onto the orbital is x-axis. That's why this was named as px. When the probability of finding the electron is maximum onto the y-axis, will term as py orbital. The probability of finding the orbital is maximum onto the z-axis, so it will be termed as pz orbitals. So we get it as px, py, pz. That means p orbitals are having three suborbitals, which we termed it as in the quantum number as +1, 0, -1, magnetic quantum number, where we specified it, the magnetic quantum number m. For pz, 0, px or py, plus or minus 1. So we got it as three different values, we got it as three different orbitals, and the names were written as px, py, pz because the probability of finding the electron was maximum onto that axis. So it was termed as px, py and pz. Similarly, when we go it for d orbitals, we termed it as we are having it as double dumbbell shape, right? That means the lobes that we are going to get it, they are going to be properly in the two different formats. Again, x, y, z. When the probability of finding the electron is between x and y, it's a dxy. Now here there is a very first time you will be facing the problem when it is in 2 dimension and in 3 dimension. Once we will study all of them, and then I will try to understand what is the difference that we are going to get it. This is for dxy between x and y. If I plot the axis between y and z, it will become yz orbital. When we plot it as between x and z, dxz. On x and y, dx square y square. On z square, and then spherical, dz square. Now see here, these are the shapes that we just plotted it on the 2 dimension. But if you see it in all the three, this is z, this is x, this is your z, this is your x. I have plotted in all the cases in between them, but because it's a 2-dimensional figure. It's a 2 dimension. I have just plotted on 2 dimension. It's not a 3 dimension. So this particular axis is drawn commonly, right? On the 3 dimension, if you go it for putting it all the 3 axes together, if you take it as the 3 different pens, place it in front of one another and try to get the answer, you will be able to see the shapes properly, right? Here we wrote it as between x and y, between x and z, right? Now between x and z means what will happen between here, between x and z? I plotted it on Y, but actually the electrons are not onto the Y. Y orbital is over here, front to back, but on the 2 dimension it is been plotted over here. So it is between X and Z. Only it looks as if it's on Y, but it's not. It's a 2-dimension figure. So while we are studying it, drawing the diagram is on the 2 dimension, while studying is on the 3 dimension. So make it sure that you don't get it any problem for it. Okay, you will have to draw these diagrams. Okay, as well as F orbitals. The shapes are complex. The shapes of the F orbitals are complex. They are not fixed. The reason is these orbitals, they are having more than 3 axes where we will be having a probability of finding the electron. So their probability of finding the electron is yet not been decided or not been fixed, and that's the reason why their shapes are not specified and they are written out as complex shapes. Right? So for S we are having it as an spherical, for P dumbbell, for D double dumbbell. For S we don't have angular nodes. For P we are always having 1 angular nodes. For D we will be having 2 angular nodes. Radial nodes, they depend upon the energy level, principal quantum number n. Depending upon it, the number of the radial nodes can be calculated. For that, the formula we are having, it is a n minus l minus 1. Right? These are all the points that you will be having it as an under the heading of shapes of orbitals. Right? There will be a maximum number of objective questions. One of the theoretical question that can be there for you is in the form of draw the shapes of orbitals. So how we plotted it, similarly you will have to plot the shapes of orbitals. Thank you. Today it's enough for this lecture. We'll study in the next lecture related to the energy levels and how to write the electronic configuration of any given atoms in the next lecture. Thank you.